Should I do, Dr. Shastri? Should I? I think Biswajit can become unmute himself as well. I think. Biswajit.
Yes, sir. Now we could not do before. Yeah, I will start. Yeah.
Start now.
Yeah. We are going to start. Good morning to our today's speaker, Professor Dominic Tildesley, and good afternoon, participants from India. Every year, across all CSIR labs, conduct summer research training program where students come and do experiment themselves. This pandemic situation hindered such activity, and Dr. Shekhar Simande, DGCSIR, conceived the idea of online summer research training program. And under the leadership of Dr. G. Narori Shastri, Director CSR NIST, is coordinating the program of SRTP 2020. Total 16,000 applications are received across the India, and all are given opportunity to participate this online SRTP 2020. We are very fortunate to have you, sir, in today's session of Eminent Scientist lecture. Now we welcome you and requesting our director, sir, to introduce our speaker. What do you, director, sir?
Good afternoon, all of you. Good morning, Dr. Dominic Tildesley. And I wanted to tell for the benefit of the participants that the summer research training program was more driven by the call of the people who were given a very short notice, only about a week, and a large number of people have applied. And at that particular point of time, we were very grateful to Royal Society of Chemistry. Dr. Rajesh has come forward and then say that we are also with you. And many other speakers are able to accept our request and then come forward and then participate in this program. And I would like to bring to the notice of the people that this is a program which is not just a series of online lectures. It has a project where each student will be given a mentor, and there are some issues which are involved in managing more than 10,000 students. But somehow successfully we are able to get students in 14 different projects of CSIR NIST, and 37 other laboratories have also come forward to give the summer projects. And other features of importance in this particular summer research training program is that we are able to get some competitions for the essay writing, slogan writing, and on sustainable developmental goals. And also electrician competitions were made, and people can make videos and then send. The one more important feature is more than 250 videos are being prepared, which will describe the working principles of many instruments that are being used in chemistry, physics, biology, engineering, and even biomedical applications. So we are very, very fortunate with us, Dr. Dominic Tildesley, who is a very, very accomplished theoretical chemist working on large systems and then looking at industrial applications of them. And Dr. Tildesley is currently associated with University of Southampton, but he has provided a very good leadership as the President of Royal Society of Chemistry, and also the former President of the CECAM. CECAM is an organization which is really very much on the forefront to provide training, and we are very lucky to have Professor Dominic Tildesley with us. And I, on behalf of all our SRTP team, on behalf of Royal Society, Dr. Rajesh Parishwar, welcome Professor Dominic Tildesley to give his exciting talk on great expectations a chemist takes to modeling. Expectations are as important as imagination. Skill is important, imagination is important, and I think dreams and expectations are more important for us to drive forward. And we are very much looking forward to listen to you, Professor Tildesley, and the floor is yours. Thank you very much for accepting our request and then becoming a part of this very, very important program. And we seek to your support in the coming years so that we can do something for the popularization of science and then inculcating the scientific temper internationally. Thank you very much.
Thank you very much, Director. Good morning, everybody. Thanks to the Royal Society of Chemistry for helping me to organise this. I'd like to talk to you this morning about my adventures as a modeller over the last 40 to 50 years. These begin in the 1970s, and you can see here Led Zeppelin. This was the group that sung Stairway to Heaven when I was in my first year at university. And then on the other side is me now, with my daughter taking a break this January in Kochi in India on my way to give a talk at the VIT. So my career has spanned the time from 1970 right up to the present. It began though in 1973. My love affair with computing and software began when I was a second year undergraduate at Southampton. I had the opportunity to work that summer with IBM in their development laboratory at Hursley. We were doing top secret work on the hardness of ferrite for computer memories, and we were locked into this compound surrounded by barbed wire. Now, I haven't done much thinking about the hardness of ferrite since those days, but during that time I learnt to program. So I did my first computer programming on a little teletype machine using the language APL and then Fortran. And after my first taste, I was completely addicted. I had meant then to combine the two loves of my life, which was computing and chemistry, by doing a PhD with Professor Sir John Rowlinson in Oxford in 1976. And I started work on trying to understand the structure of liquid nitrogen. It's a very simple system of diatomics. We were able to simulate on the computer 108 such molecules. We used what's called the Monte Carlo method, so named because of the use of random numbers in order to generate equilibrium states in a variety of different ensembles. Each day we would work in the morning on our theory and then carry a large box of 1,000 to 1,500 cards across to the gigantic ICL machine, the 1906A. There, the cards will be read and then sent to Manchester. I got 20 minutes of computing time every evening. So these computations took months to complete. They were slow and steady. We tried always to compare with experiment. I was king of all I surveyed, but what I surveyed was pretty slow and pretty steady. And in fact, quite unreliable because the computations that we performed would often fail. As I say, we carried our cards in very large boxes, and in a bad wind and one of the cards blew away, we wouldn't be simulating 108 nitrogen molecules, we would only be simulating 107. So you can ask, what led me when I became elected as president of the Royal Society of Chemistry to make the following statement in my inaugural lecture, that the speed and development of computers is now so rapid and the advance in modeling and informatics so dramatic that in 15 years, no chemist will do any experiment at the bench without trying to model them first. So what had changed from those days in the 1970s when I was able to simulate 100 very simple molecules on a computer over periods of months, to making this probably one of the most important techniques that chemists will be using in their careers in the future? And I think there are 4 reasons for this change, which I would like to try to outline in this talk. The first of these is the speed of the machine. The second, the imagination of the theoretician. Then the collaboration with industry, the foil that industry has, so that this enables us to push these methods forward. And last but by no means least, the enormous rise in the power of big data and the building of machine learning, which helps us as chemists to tackle some really very difficult problems on a sensible timescale. So let me try to deal with each one of those 4 in order. So first, you can say that the first computer simulations, Monte Carlo simulations, were performed at the Lawrence Livermore laboratory on a descendant of the machine like the ENIAC in 1946. This was developed at Aberdeen, Maryland to calculate shell trajectories during the Second World War. It contained 20,000 vacuum tubes, and it ran at the speed of 1 flop. A flop is a floating point operation per second. When it went wrong, you simply wound the calculation back, replaced the valve, and continued. By the time I started in 1976, the biggest supercomputers that we had available were the CDC computers. These would run at a maximum of 36 megaflops, 36 times 10 to the 6 floating point operations per second on hand-compiled codes. And as I say, one could get maybe 20 minutes of time on these machines during the course of a day. At present, I'll give you an example here of a European machine. This is the IBM Blue Gene Q system installed at the University of Jülich. The most recent system contains 8 racks with 32 individual computing elements on each rack, each with 32 processors. And it has a peak performance of about 1.6 petaflops. A petaflop is 10 to the 15 floating point operations per second. So the speed of increase has been immense. In fact, the speed of computing really doubles every 2 years. And this is Moore's law, which enjoyed its 50th anniversary in 2015. I've plotted on a log linear scale time versus computing speeds here. You can see down right back down in the 1990s, speeds of a gigaflop. And now as we move, I expect to cross the exaflop barrier this year. That will mean we'll be able to form 10 to the 18 floating point operations per second. The speed increase will not be achieved just by cramming more components onto a chip, but by really ingenious use of parallel computing methods. Actually, you can see the fastest computer there is the red line, but I'm more interested in the pink line, which is about 6 years behind, which is the average speed of the top 400 computers in the world. And you can see that roughly machines that are in reach of top class universities will be performing petaflop calculations this year. I'm talking about machines that we could expect to see almost in every IIT in India, ready to access petaflop performance with cores of over 3 million components. So to be competitive on the world stage, universities and industrial partners will need systems of this scale. I mentioned earlier that massively parallel computing was going to be extremely important. Here we take the system, the molecules we're interested in, and we distribute them across a large number of different computers. Space is distributed across 9 computers in this simple example. And to calculate the force on atoms in the central box, we only require information on those purple-colored 8 surrounding boxes. This is all held on the same processor. The only time we need to swap information between processors is at the very edge of those boxes, and that happens once in every kind of time step. This means that we can perform massive calculations in parallel by distributing the atoms that we have across many different computers in a domain decomposition. This is going to be an extremely important technique for the future. So you'll be pleased to hear that heartened that it's not simply the theoretical development and the technology developments, but the irrepressible imagination of theoreticians or computational scientists, which has left its mark on the intervening 40 years. One thinks immediately here of the 2 Nobel Prizes in chemistry awarded for modeling. Systems such as the following lipid bilayer, with a small protein inserted into the bilayer as an ion channel, can now be simulated using molecular dynamics. We know the positions of the atoms. We know their velocities because we know the temperature of the system, and there's a Maxwell-Boltzmann distribution of velocities. To calculate the accelerations, we have to know the forces on the molecules. And to know the forces, we have to have a force field. And one of the most important developments has been in force field development. So this is a series of terms which describes the interactions between atoms in a system. First of these is bond stretching, which we can see there, worth about 300 kilojoules per mole. The second is bond bending, worth about 100 kilojoules per mole. Then we have the kind of torsional or bending potentials, moving from cis to trans, worth about 10 kilojoules per mole. And then we have non-bonded interactions between atoms which are not directly bonded. The most important of these really is the dispersion-repulsion interaction. And that's where the electrons stop, 2 atoms sitting on top of one another. And then we have the electrostatic interactions, repulsive interactions between charges which are the same, and attractive interactions between charges which are different. The catastrophe of a negative charge sitting on top of a positive charge is prevented by the dispersion-repulsion interaction. Now, there are excellent force fields available for many different systems. Systems such as water, metals, ionic liquids, proteins, DNA, sugars, clays, even electrodes, in almost all systems of importance. And these were, the Nobel Prize in 2013 was awarded to Karplus, Levitt and Warshaw for the development of these systems. And these systems can be used in complex and simple systems. This is a simulation of a set of water molecules. And it's a rather special simulation because you can see the making and breaking of the hydrogen bonds in the liquid water. Here we have a time step of about 2 picoseconds, 2 times 10 to the minus 15 seconds. And we're simulating maybe 10,000 time steps here. And the beauty of this simulation is that not only does a classical force field describe the interaction between the oxygens and the hydrogens, but also we include the electrons in this calculation. Electrons, of course, are extremely important for chemists in the making and breaking of bonds. And when we include electrons, we have to move away from a classical description to a quantum mechanical description. And this has been allowed in molecular simulation by the wonderful award of the Nobel Prize to Walter Kohn for the development of density functional theory. And using the work of Roberto Carr and Michele Paranello and the enormous body of work now on ab initio, or first principles molecular dynamics, we can include density functional calculations into our classical molecular dynamics simulations to simulate situations where the electrons are important. I want to give you one simple example of another wonderful methodological development, which I called chemical alchemy. This is about the calculation of the binding of small molecules into proteins. And we might be interested in the binding of a molecule B from aqueous environment into the middle of the protein, and a binding of molecule A from an aqueous environment into the middle of the protein. And what we have here is a cycle. So if we want to understand the difference between the free energy of binding of A and B, then all we need to do is to calculate the other 2 vertical arms of the thermodynamic cycle. How do you change molecule A into molecule B in an aqueous environment? And how do you change A into B when it's bound to the protein. Now, that's not something you can do in the lab, but it is a piece of alchemy that you can do on the computer. And this wonderful technique of morphing one molecule into another and calculating the Gibbs free energy, the enthalpy and the term associated with the entropy, was developed by Bill Jorgensen at the University of Yale in 1985. But really interestingly, you can see here that it comes from a theoretical development by an American scientist, a great scientist, Robert Swanzik, who died in 2014. And in 1954, he showed how it would be possible to calculate the free energy difference in a simulation. What you do is you start with your atom A and you morph it slowly but surely into atom B. Now you run a simulation using the force field of atom A, but you pretend it's actually atom B, and you calculate the energy associated with B and A and that energy difference, delta UBA. Then the free energy difference is simply the logarithm of the average of the exponential of the internal energy difference. It's a really hard calculation to do. You can't do it in one leap. You have to do it in a number of small steps, but it can be extremely accurate. Now, you notice that this was developed in 54, but if I just remind you that it was right, it took another 30 years before Jorgensen was able to use this method in a computer simulation. So you have to be patient to take these theoretical ideas and push them through. Anyway, this has been really wonderful because it's been used, and I'll give you an example here, of an inhibitor for the HIV-1 transcriptase enzyme. This is important in HIV therapy. And a particularly important therapy has the molecule on the left-hand side with X equal to chlorine or fluorine. Notice that that molecule has a cyanovinyl group. Now, this is a concern because such an active group could lead to electrophilic addition and a covalent modification of the protein, which we want to avoid. So a number of bicyclic replacements have been tried on the computer. So we've taken all of the systems in which X, Y, Z, and W could be carbon, nitrogen, oxygen, where R and R primed are hydrogen, and R double primed is a cyano group. And doing computer simulations using this free energy morphing chemical alchemy method, we're able to show that the system shown on the left-hand side, where W, Y, and Z are carbon, and X is a nitrogen, is a particularly stable and a particularly active inhibitor, offering an EC50 value, the dose which is required to obtain 50% of the infected cells, which is as good as any that we have. So this is a remarkable application of this kind of computational alchemy method, and gives you an example of the kind of sophisticated ideas that theoreticians have been using and developing in order to apply simulation methods, Monte Carlo methods, molecular dynamics methods, density functional methods, to pharmaceutical and large systems of real interest. In my next idea, I just want to talk about the relationship a little between industry and academy. In my own career, I had the wonderful opportunity to work for Unilever, having worked for 18 years at the University of Southampton as a professor. I moved in to look after physical and measurement sciences group for the company. And I just want to say that UK upstream chemical industries and downstream and upstream chemical industries contribute approximately £260 billion in added value to our economy, which is about 21% of the UK GDP, and support over 6 million jobs. However, large multinationals and pharmaceutical industry have been quite slow in adopting and using computational methods compared, say, to the aerospace or the transport industries. One of the reasons here, I think, is getting the right relationship between industry and academia. I've shown you on the left-hand side here a wonderful painting in the Leverhulme Art Gallery of Billy Lever, Lord Leverhulme, who was the founder of Unilever. And he is talking to one of my colleagues. I've called him Professor Prof. So as usual, Professor Prof, who's interested in gravitational waves, is simply asking Sir Billy, interested, would he like to fund his research? And Sir Billy is saying, would you like to stop working on gravitational waves and help us to develop and market a new kitchen cleaner? So that kind of conversation is not going to be very successful. So in order for good collaborations to work in industry needs to take a long-term view to ask some basic and fundamental interesting questions of academy. And academy really does need to be able to switch its attention from the things that are immediately interesting to genuinely try to answer some of the questions that industry has put onto the table. I've shown this as a kind of fencing match, industry and academy. And I want to share with you one example, which comes from the work I did at CECAM with my colleague Caterina Mendonca and Agilo Padua and Patrice Malfray, looking at the issue of ionic lubricants. So lubricants are used in factories to really oil the wheels between the two great cogs, as shown on the bottom left-hand side of the slide. These cogs often move at very fast speeds, shearing velocities up to 1 meter per second, which is enormously fast. And they have really enormous pressures between the cogs of order gigapascal. And so these lubricants which need to be used have to be extremely stable and have to have a very low friction coefficient. The kind of lubricants that we were interested in this European projects were liquid lubricants composed of ionic liquids. So here we have a typical ionic liquid, a trimethyl ammonium alkyl sulfonate. And there are thousands of combinations of anions and cations which we could use. I have to remember that these liquids are effectively melts. There's no water involved here. And we're interested in issues such as viscosity, melting points, miscibility, and this is strongly dependent on the ionic structure. So the main idea in this work was to do some simulations where we would confine an ionic liquid in between two metal surfaces. And these metal surfaces would be composed of iron. We would use a quantum mechanical model for the iron. The outside layer of the iron would be mobile, the inside layer would be rigid. And we could actually build deformities and asperities on the iron to understand the fact that the surfaces are not perfectly smooth. We would then measure the pressure, Fz, between the two surfaces. And this is very important because Fz is the normal pressure. Now, we can also measure the pressure which is due to the force in the Z direction, but acting along the direction tangential to the surface. Now, when the surfaces are still, that force is zero. But if you move the surfaces, if you move the top surface with respect to the bottom surface, or equally either surface with respect to one another, then that off-diagonal component of the pressure tensor becomes non-zero. And it's the ratio of Pxz to Pzz, which is simply the friction coefficient. So I'm going to just show you a simulation here of the methyl alcohol sulfonate. So here just to put this in perspective, the red atoms are the sulfonates, the blues are the ammonium head groups, the greys are the alcohol tails in both the anions and the cations. There's an ionic melt. You can see I've actually built in some asperities onto the surface. I'm moving the top surface at a speed of about 1 meter per second, and I am measuring the pressures. Now, what this enables me to do is to make an estimate of the friction coefficient, which compares very favorably with experiment. But the real beauty is not to get an exact value for the friction coefficient, but to simulate many different ionic liquids and put them in order. Then, given the friction coefficients we calculate, we can make suggestions to the experimental group about what might be the best possible ionic liquids to use under these circumstances. Now, these are very fast moving wheels, 1 meter per second, very high pressures, a gigapascal. We've also been doing a lot of work recently on trying to understand the friction between polymer brushes. This is important if you want to build models of lubrication, say for hair conditioners, or for fabric conditioners, or for surfactants and polymers which are going to be used in the lung to lubricate, or polymers which might lubricate joints. And here you need to go to much, much longer times, and you need to go to much lower pressures, from a gigapascal down to around about 7 megapascals. And in order to do that, you have to build a coarse-grained model of the system. You can no longer just look at the atoms. So you need to combine the atoms together into what I call mesoblobs, or blobs. And each blob of water here, that's the orange blob, contains about 9 to 10 water molecules. And each blob in the polymer chain represents about 5 linked methacrylate groups. So this is what we call a coarse-grained model. And one of the big advances in simulation is moving from atomistic models upscale to more coarse-grained simulation models. And again, you can simulate this. Again, we're simulating many polymers attached to the surfaces. I've just colored them as a matter of aesthetics rather than anything else. And I'm going to, first of all, simulate the surfaces when they're not moving and the polymers are just bouncing off one another. And we can check the forces are correct here by applying, with respect to the surface forces apparatus of Klein and Israeli Chile. And now I begin to move the surfaces at a shear rate of about 10 to the 5 second to the -1. And you can see the polymers stretching out and forming a really beautiful lubrication layer. At the boundary, the top surface and the bottom surface are now moving smoothly over one another, and even opening up some gaps. So that's the kind of work we've done, and we've been using this work to ask ourselves questions like, how strongly charged can the polymers be and still act as really successful lubricants? What is the length of the polymer chain? How important is that in lubrication? Are surfaces best lubricated when they are pushed hard together, or when they are in fact at a very low normal compression? And we've been answering those questions in a series of papers with my collaborator Patrice Malfray at the University of Clermont-Ferrand in France and at CECAM. Finally, I want to say that one of the biggest changes that we've seen in this time is not just in the speed of computers and the complexity of systems that we can simulate, but also in the use of models which don't have a reference to an underlying Hamiltonian or an underlying force field. These models are just going to correlate molecular properties with observable properties. These techniques are often called QSARs, or quantitative structural activity relationships in chemistry. Or these days, the more grandiose titles, machine learning on big data, is often heard to resound in the halls of government and funding agencies. I want to give you an example of a problem which we tackled in Unilever with the team, led by Ian Stott. And in this problem, we were asked to design some new antimicrobials which we could use in household cleaning products. And the idea here was to build antimicrobials from peptide chains. These peptide chains are thought to actually form a strong alpha helix. We chose small peptides, about 10 to 15 amino acids. And we chose them of that length so that they would actually penetrate the wall of the bilayer, that they could sit astride the wall of the bilayer. And we did lots of experimental measurements on these to develop what's called a training set. So we determined the P kill against 2 bacteria, Stratorius and E. coli. Now the hypothesis was that the peptides would fold up into an alpha helix with the red or the oil-like residues on one side and the blue or the water-loving residues on the other side. And then these peptides would form a cluster, a hexamer, with a hydrophobic exterior and a hydrophilic channel, which could then be used to pump ions into the cell membrane and to kill the cells. So we had to use our imaginations to develop something which would tell us how well these proteins folded up into these helices with hydrophobic residues on one side, hydrophilic on the other. And we developed a function called the hydrophobic Sine function, which is a function of the peptide structure. I won't go into the details of that, but it's a single number which measures how strongly that folding up process goes. Let me give you two examples. This is for the kill of Stratoris. Here at the top is a really good example where you can see the hydrophilicity that follows a really beautiful sine curve. So the residues are hydrophobic, hydrophilic, hydrophobic, hydrophilic, hydrophobic, hydrophilic. And that is likely to fold up and give us a really good channel. And indeed, the log kill is very high, it's 7. So that makes us very happy. Below is an example of one where the folding, where you might think that the residues are going to fold quite well, but you can see from the fit to the sine curve that it doesn't happen quite so well in this case. It's not quite so straightforwardly hydrophilic, hydrophobic, hydrophilic, hydrophobic. And that makes us unhappy. And that gives us a Stratoris log kill, which is much lower, about 0.3. So what we do in these techniques and methods is to build a neural network. This is very simple. You have an input layer, and the input data can come either from an experiment or indeed from simulation or modeling of collections of molecules or single molecules. It might be something like the molecular weight, straightforward, or the solubility in water, or the dipole moment of the peptide, or the overall hydrophobicity, or in our case, importantly, the hydrophobic Sine function, which I've just shown you. It also depends on the length of the peptide. Now, in a neural network, you have a number of hidden layers and a number of weights which you can adjust in those layers. So from a given input, that's for a particular peptide, you should be able to get the output, which is the p-kill against the bacteria. So what you do is you use your training set to adjust the weights in the middle blue layers to make an accurate prediction. And one of the beautiful and interesting things about this method is that if you've chosen the wrong set of inputs, suppose that solubility doesn't matter, the data, the neural network will soon show you that by making it clear that it makes no difference to the quality of the fit. Now, here's what we do. We measure or model the dependent variables, the sine function, the length. We use a neural network to obtain a functional relationship. This predicts p-kill, and we use a training set. We can now invert the model. We use something called a genetic functional algorithm. It doesn't matter too much. It just enables us to go back and invert the model to make predictions of new peptides, which will have a high log kill. We make as many of those as we can, which are as diverse and different as possible. We make some of these new peptides that are predicted to be active and that are diverse. We measure the log kill of these new peptides and we add them to the training set, and we really fit the neural network. And we go around that cycle 3 or 4 times, improving the set. Now, in this work, we were able to generate a number of new peptide sequences. I've shown you a few of them there, which had a very high predicted log kill from the model. And actually, when you measured the log kill after 3 or 4 cycles, after the 4th cycle, these peptides were also extremely good in the lab. So they might be able to put them into a particular product, depending on safety and all sorts of other issues. So the project requirement was to find log kills greater than high, and we were able to use this neural network with a training set, with an inversion and a cycle in order to do exactly that. Now, the beauty of this method is it's fast. It doesn't require the vast amount of computing time that some of the original simulations I described require. And of course, in industry, you always used to joke that there are only 3 time scales of interest: coffee break, lunch break, and very serious problems overnight. after overnight, the people who were funding the research in industry often lost interest. So we did need to develop these methods, which were fast and enabled us to make really good, simple predictions. So I just want to refresh what I've said over the last few minutes. There has been an enormous increase in my lifetime of 10 to the 11 in computational power and a corresponding increase in storage. To put this into perspective, the only thing I think which is changing more quickly in science is our ability to actually measure the genetic sequence of all sorts of human organisms. But this increase in computational power is very fast, it's very real, it's continuing, and it will continue because of our ability to use parallel machines. When I talk about using parallel machines, I just want to stress that you don't actually have to run enormous calculations. You can run many smaller simulations with different conditions at the same time. For instance, to produce the data for one of our neural network models. So that's been a huge breakthrough. There have been significant methodological breakthroughs. So both in terms of the Monte Carlo method, which uses random numbers to create all sorts of possible configurations which are in the correct ensemble and equilibrium, or in molecular dynamics. We now can simulate up to around about 15 million atoms. Saw a beautiful simulation recently of a water droplet with many millions of atoms. What is more important, we can begin to tackle problems in chemistry, which involve the use of electrons, because we can now do simulations using density functional theory, which solve not just the Newtonian equations, if you like, of the nuclei, but also the quantum mechanical calculations of the wave functions. This is extremely important for us. These calculations on quantum molecular dynamics are still at the leading edge because they're still very expensive. But a beautiful development has been the combination of simulations where you do molecular dynamics using quantum mechanics of one region, surrounded by normal classical molecular dynamics, which is much faster for the reasons which are perhaps a little bit less interesting. So this combined QM-MM calculations are going to be very important in the future. Another thing which has really improved has been the hunger of industry to use these methods as a tool for economic growth, the speed of their own economic growth. And this has been brilliant for us because it pushes us along and funds some of our basic research. We simply have to remember to be asking the right kind of questions, both in industry and in academy, in order that we can have a meeting of the minds. In this kind of calculation, because we need to simulate for very long periods of time, the whole area of coarse grading, whereby you stop thinking necessarily about atoms and molecules, but move to particles, the development of new techniques such as the lattice-Boltzmann method and dissipative particle dynamics are extremely important. The ability to move between different length scales in simulation will be one of the really important developments over the next 10 years. And then finally, I talked to you about the new paradigm of machine learning and the use of data models to capture trends in experimental and simulated output. This is fast, it's extremely valuable, it's self-correcting in the sense that if you choose the wrong input variables, it will soon let you know. And you can improve your training set all the time to give you a better correlation. So those, I think, are the 4 pieces of information which enable me to go back and say I do not regret making that statement when I became president of the Royal Society of Chemistry. I think in 15 years, chemists will always use some kind of modeling, either simulation, quantum mechanical modeling, data-driven modeling, before they begin experiments. And we will see computers and models at the bench. So to finish by saying that actually, I'm well aware that chemists and biologists have always modeled. If you only walk through any chemistry lab, you will see people modeling by drawing on the sides of the of the fume cupboard. These kind of Banksy-esque sketches of reaction rates, reaction pathways, possible intermediates, all sorts of information, which is to remind the chemist about what is going on inside the fume cupboard. And I think that all that's happened in my lifetime really is that the only thing that's really changed has been the power and the sophistication of the calculations. We no longer have to make sketches on the wall of the fume cupboard. We can actually bring our computers into work and work very closely with the experiment in the lab. And of course, since the unfortunate business of lockdown, we can now do all of our work from home. So I want to leave it there and to hope this has been useful for you, to thank you very much and to wish you a very safe and productive period over the next few months. Thank you.
Thank you, sir, for the exciting lecture. Now I hand over the agenda to Monty for the question and answer session. Monty, please take over.
On behalf of our director, CSIR NEAST, and all the SRTP members, I thank you, sir, for your insightful presentation. It was indeed a great pleasure for all of us to listen to you, sir. So with your permission, we would like to go forward with the question and answer session. There are a lot of questions and we would sum up to just 2 or few questions. Sir, should we proceed?
Absolutely, I look forward to it. Ask away, please.
So the first question is from Hemant Kumar. How do we differentiate between series and parallel computing in molecular dynamics and how to use it?
I'm sorry, could you just repeat the first part of the question for me?
How do we differentiate between series and parallel computing in molecular dynamics and how to use it?
Okay, so I mean, normally when we perform molecular dynamics, we would do it first of all on a serial machine, yeah? And one thinks there of at each time step, the big part of the calculation is calculating all of the forces on one molecule, all of the other forces which are in its immediate vicinity, all the other molecules in its immediate vicinity. We do that calculation, we move the particles forward over a small time step to a new position, and then we repeat, and we go on doing that many, many times. The power of parallel computing is that we can speed up that calculation of the forces, and that is what speeds up the calculation. So essentially, we can divide the molecules as they are distributed in space, or the atoms as they're distributed in space, across a large number of different processes. Then because the range of the forces is finite, we can deal with all the calculations of the force on one atom on its processor. And we can do that in parallel, and that takes the calculation from a calculation which depends on n squared, where n is the number of atoms, to a calculation which depends only on n, or perhaps n log n. And so much faster. So this domain decomposition is a really important way forward. And there are other structures. You can decompose the loop structures in the calculation. But I think now, in order to get maximum speed and to study the systems of real interest, we really will have to move to parallel computing in the future. And I think that is not a challenge, it's simply a big and interesting opportunity for us. Okay.
Yes, sir. Thank you so much, sir. The next question is from Madhupriya. In market, there are more edible oil. Whether we can find which oil is good by calorimetrically?
Yes, so I think that you can certainly, these days, take a simple chemical reaction, well, not such a simple chemical reaction, so that's oxidation, and make a prediction about how much energy is going to produce, and therefore, in some senses, do a theoretical calculation of your calorimetric experiment in advance. Of course, that's easy for me to say, but it's actually quite difficult to do. because one, you've got to be able to understand the energies of the reactants and the products. You've also probably got to be able to understand something of the transition state in the reaction and its energies. You've then got to make possible calculations of the free energies in order to give you the equilibrium constant for the reaction, or even through transition state theories, some estimate of the rate of that chemical reaction. And of course, the systems that your questioner is talking about are not simple systems. They are often mixtures of systems. So you might be able to, if you have a 5-component mixture, to do this calculation on each of the components. But even then, the overall reaction that you have to study might not simply be a simple combination of the individual oxidation reactions on individual components of the fuel, but might be a complex problem associated with the mixture itself. So start simply, do the calculations as easily as you can on simple systems to give you a guideline as to what experiments would be interesting, which particular oils it would be interesting to study and to think about. Okay, that's probably the best I can do on that.
Thank you, sir. We could not agree more on how nicely you have highlighted each and every areas throughout your informative lectures. And sir, I would like to say you that all the live platforms are filled with appreciation and a lot of comments. And sir, there were a lot of questions for you. And so we will sum up all the questions and we'll prepare a thank you note for you, sir.
Yeah.
Sir, now
I can't promise to answer all of the questions, but I will do my best to answer as many as I can. Okay?
Yes, sir. Thank you so much, sir.
Okay.
Sir, now I would like to hand over the session to Orup Roy, sir. Sir, over to you.
Yeah. So thank you very much for giving such an elaborate talk on the history of computational modeling and its exponential development, as you mentioned it, in the order of 10 to the 11, and its growth over the years. And for discussing the relationship between industry and academia, especially with respect to the computational modeling. Of particular interest was this peptide modeling that you mentioned and your prediction of the p-kill and log kill, which was almost matching with the experimental results. And such kind of short peptides and designing, I have appreciated this because I do peptides and peptides. So it was really a lecture which was of different flavor. I believe that all the participants were talk. On behalf of the whole team, thank you once again for sparing your valuable time and ignite the young minds. The participants were students and who joined the lecture through all the 3 platforms, Zoom, YouTube, as well as Facebook Live. So we would like to take this opportunity to thank Dr. G.N. Shastri, our director, for his mentorship and able guidance. And we also sincerely acknowledge the whole SRTP team for the successful conduct of this session. Thank you all for your participation. Thank you, sir, for taking out your time and giving such an inspiring lecture. Thank you very much.
Thank you all very much indeed. It's been a pleasure. Thank you.